I've put together this video for a bit of speculation and a bit of fun, but also to be informative as well. It's a few personal takes on the nature of breaking gravity's bonds here on Earth. I believe that what stands in the way of humankind's evolution as a spacefaring race is not interplanetary or interstellar travel, but just being able to fly cheaply and safely from the ground into space. I'm not going to discuss all the different suggested methods for doing this here. There have been many suggestions, from conventional rocketry to space elevators to giant guns which fire a vehicle into space. Instead, I'm just going to focus on some facts and ideas which I find interesting and explore these. If you're interested in some of the more far-out concepts, I would recommend having a look at Andrew Nowicki's site as a cool place to explore some of these. One interesting thing to bear in mind is that if a new form of power supply becomes available, which can either generate or store and release large amounts of energy, then a whole new set of potential technologies will become available. For example, these might involve coupling to natural or artificial magnetic, electrostatic or electromagnetic fields, either generated internally in a craft or beamed from the Earth or from space, or alternatively using electrical or electromagnetic heating of the air in a jet-like duct. Over the years, as people have considered different methods of gaining access to space, there have been quite a number of false leads and dead ends already. A good example of one of those is the thrust systems which seek to convert rotational motion into unbalanced linear motion. One episode which brought these sort of systems to the fore was a claim by Professor Eric Laithwaite of Imperial College London that a lifting force could be produced by gyroscopic motion. Laithwaite demonstrated how spinning up a heavy disc on a rod allowed him to lift it over his head, whereas under normal circumstances it would be far too heavy. And you can see this experiment repeated on YouTube. You might also think of a similar rotational system with a lifting force which is present in a centrifugal governor for steam devices. Such effects are difficult for us to understand because rotational systems are often counterintuitive, and we generally don't encounter them in everyday life. We can demonstrate, however, the idea of rotational to linear momentum transfer if we think about three gears, each one of which has a weight attached to its rim, as shown in the diagram. The small ones are half the diameter of the larger ones. As the mass spins round at the edge of a gear, it produces an unbalanced force, rather like the misdistributed load in a washing machine, which causes it to hop up and down. When the three masses align, the forces are all in the same direction and add together. And this only occurs in one direction when the masses are pointing upwards, as shown in the diagram. So at first sight, it would seem that there really is a large force acting in one direction as the gears spin. But actually, we can see what is really happening if we plot out the forces for the individual gears. Although point A is higher than point B, the area shown as 1 is the same as 2, so the impulse is the same, and the momentum over the whole cycle is conserved. If we were to put this contraption on a little boat as shown, it would make progress because the instantaneous force in the direction A, combined with the low drag of the pointed end of the boat, would cause it to move in that direction, but not move as far backwards because the force is smaller and there's more drag backwards, giving the false impression of momentum transfer. But of course, this wouldn't work without the drag of the water around the boat. All the other rotational systems are defeated by similar considerations. For example, a weight moving up and down on a rotating arm. If we moved the weight up to point A at the top, and then closer to the centre at point B, we would similarly expect an unbalanced force. But this time, the effects are counteracted by the forces required to move the weight and their reactions. In Laithwaite's suggestion, The bogey is the fact that a central pillar, the person holding the rod, is required in a fixed position, around which the spinning disk must be rotated. If we remove this, the system doesn't work. So let's turn to some more interesting and useful effects. First, let's look at some frustratingly simple figures. To get to a height where one has essentially cleared the Earth's atmosphere means travelling upwards to, let's say, 500 kilometers above the Earth. Since this takes an energy given by mgh, for a 100 kilogram weight, the energy required is 100 times 9.81, which is the acceleration due to gravity, times 500,000 meters, which is 490.5 megajoules. Since power is equal to energy over time, that's a power of, let's say, 800 odd kilowatts for about 10 minutes. Basically the power generated by a large industrial motor. Of course, this doesn't include the kinetic energy necessary to reach orbital velocity, which at a couple of hundred kilometers might be about 7 kilometers per second. We've often told, in fact, that there is an escape velocity necessary to leave Earth, but actually, any force which is slightly greater than your weight, for example, will cause you to accelerate upwards with an acceleration of that force divided by your mass. So even generating a few newtons of force in excess of your weight will send you indefinitely skywards. Furthermore, supposing we continue travelling until high above the Earth, we could then simply fall back towards it and gain orbital velocity in that way, and only have to generate a force necessary to move your craft out of the way of the Earth in the x direction as shown in the diagram. So, using a rocket to accelerate a payload to high Mach numbers in order to escape isn't actually technically the only theoretical way of leaving Earth. So, if it's as easy as that, why can't we simply just fly into space? Well, I'd like to discuss this now. The density and pressure of air in the atmosphere both decrease roughly exponentially with height. At 100,000 feet, which is 20 miles or 30 kilometers up, we are above about 99% of the atmosphere. And coincidentally, this height acts somewhat like a loose barrier to flight. It's roughly the height at which the highest gas balloons can operate, because above this height the air is not dense enough to sustain buoyant flight. It's also roughly the height at which the U-2 spy plane operates. This plane is basically a comparatively slow glorified glider with a single engine, and here the air cannot sustain lift on the wings. In contrast, another spy plane, the SR-71 Blackbird, can travel at 3.5 times the speed of sound, but when it reaches this altitude, the lack of air means that its engines cannot operate properly and burn their fuel. The barrier effect is partly due to the comparatively sudden halt of dense air, due to the exponential decrease mentioned earlier, but also because a low density of air means that it stops behaving like a normal fluid, which we call a continuum system, and the molecules are so far apart that they stop feeling forces between them, and start behaving like discrete, unconnected entities. What's important about this barrier is that it stops us simply being able to fly into space. Indeed, before the advent of a rocket, no one knew that this was even possible. This is because it falls into a class of problem which have no natural precedent. For example, we can be sure that artificial intelligence is possible because nature has already made intelligence. And we can be sure that heavier than air flight was possible because birds do it. But no one has ever seen a bird fly into space, so we didn't know that that was possible. The interesting thing is that there is power, and potentially quite a lot of it at this height. During daylight hours, the sun beats down on the top of the atmosphere with a solar power density of about 1 kilowatt per square meter. If there was a way of collecting this and converting it into thrust, which was greater than our weight, then we'd be home and dry. We could just float out of the atmosphere like a feather on the wind, and when we were high enough, drop back into orbit as we previously described. However, without air, we don't have a medium to affect momentum transfer, and we're stuck even though we have the power. Let's take balloons for example. These will rise until the gas inside the envelope and the weight of the envelope and the payload is equal to the weight of air displaced. This happens at a particular height because the air gets thinner and thinner as we go higher. Could we devise ways of allowing balloons to fly even higher? The answer to this is probably yes. For example, we could actively pump out the internal gas from the balloon envelope, making it lighter, and this would allow us to go higher, perhaps using some sort of intelligent envelope fabric. Or we could attract ions from the surrounding atmosphere to the envelope by electrostatically charging it. This would cause the volume surrounding the envelope to become denser, providing more buoyancy. The electrostatic force could also keep the envelope rigid, even if the gas inside were completely evacuated. We could even pulse the charge on different parts of the envelope and drive the ions downwards to aid buoyancy by producing a low thrust. However, although all these ideas might gain us some amount of extra height, they will not allow us to continue upwards indefinitely, because at a certain point in the atmosphere we will just run out of the air to support them. There are also other similar phenomena which we can exploit to gain some extra height. For example, many people have demonstrated ion-propelled lifter craft, which use electrostatic fields to produce an ion wind in a similar vein to the balloon systems we just discussed. However, again, once the air density reduces enough, the effect stops. Another thrust-producing effect which works at low air pressures is demonstrated by the Crookes radiometer, which molecules colliding with dark or silvered veins produce a force. Whether it's possible to use natural fields like the Earth's magnetic field or the ionized plasma layers in the upper atmosphere to produce thrust or lift is somewhat open to debate, but these fields are very small, and so this seems highly unlikely. And so there we have it. It would be nice to float free from Earth, like the feather on the breeze, and certainly there's enough power from the sun there, and all we have to do is produce a sustained force greater than the weight of the object that we're trying to lift. But presently this doesn't seem to be possible. However, if you think of a way of doing this, please let me know and we'll both make a fortune. So in the end, assuming that there are no hidden breakthroughs, we are stuck with either conventional rockets, or some reusable rocket plane not yet invented, or waiting until we find another alternative source of power, or finally trying to develop the scramjet technology that we've been discussing in some of the other videos.